Well, we're nearly there. Welcome back, everyone. Not a very big class, but I was kind of anticipating that with the inclement weather conditions. Just always know that no matter what happens with the course, there's always going to have any class we run. You can always join it through the Zoom link if you feel like driving is not a good idea. I mean, you don't want to risk your life for math. And any class that runs, we'll put down here in the recorded lectures. So I'm glad you all made it today. I hope you didn't have to work too hard with the snow removal. Any questions to start us out?
I have some questions about the text next week. So are we going to have like that kind of information paper? Oh, yeah, I saw the exam two formula sheet. Sorry.
Oh, no worries at all. I'm glad you mentioned that. Yeah, absolutely. For our next upcoming exam, I did mess up with the formula sheet on exam one, so I'm going to try a little bit harder today, or on the exam two when I write it. I want to write this exam so you can actually tear off this formula sheet and not feel like you have to send it back in. So this one will be tear offable, and the back of it should be blank, so you could also use it for scratch paper at the same time. So the sheet is going to be this one here. One thing I did learn about the way that our exams run with the testing centers and all that weird oddities is I can't necessarily put color coding on this sheet. It's not necessarily going to print correctly on everyone's testing centers. So just for the sake of the fairness, I wrote it out this way without color coding. This way it'll print correctly if you're taking it in a testing center and so on. Some of the emphasis I still left in bold, like you see here. So this basically periodic table for plotting your trig functions will be included as the last sheet. The other thing we mentioned when we were in section 6.3 is domain and range is extremely pivotal when you're dealing with inverse functions. So there'll be that domain and range table as well to support you through that end of the second exam. Other questions at the moment?
So is it just going to be just like the inverse versions, inverse functions and the drawings for exam two?
Yeah, exam two is only going to go through 6.1, 6.2. This is plotting the trig functions, and it ends on 6.3 doing the inverse functions we did last week.
Okay, thank you.
Yep, you betcha. Other questions so far? Okay, just like the other exam, this one is going to be closed calculator. We're going to open them up on the next exam. There'll be closed notes, but this will be the formula sheet provided. And keep in mind that means when you go to study for this exam, even though I am going to print this out, it'll be your last page on the exam. You might want to print this out or just maybe have it open on a different screen since you want to orient yourself really well with what information is on here if you're about to use it for the exam. Same with the domain and range tables below. And as you're studying, I would say the first place I would go to study for exam two is your actual assignment 5, the work you did here, assignment 6, and assignment 7. Knowing how to do those problems and knowing how to do them without resorting to formulas or anything like that, if you can get through those, you're on really great shape for the upcoming exam. And when I give you back your feedback for each one of those sections, take a particular attention to anything you might have missed, just to make sure you don't make those kinds of mistakes again. So I would say the homework is extremely important for preparing yourself for the exam, but they get old if doing old homework problems over and over again. And so you can also go here, the sample exam 2 problems. This document is kind of a hybrid. Some of the problems are coming out of the textbook itself, the second edition. Oh, that means I might have to double check my page numbers. I've been having page number issues. So if my page numbers are wrong, where these problems actually come from are at the end of section 6.2, but that's another spot where I have to make a double check. Double check page numbers. I hate it when they update the textbook, but updates are important. I'll just try to update things on my end as well. So aside from the page numbers, these problems right here come from the end of section 6.2, but there's also a mix of problems. In section 6.1, we did custom exercises, so I have brand new custom exercises right here. Again, I'm going to reduplicate the instructions verbatim on a real exam, and these are really great additional problems that you could study. The solutions are down below, but the best way to use this kind of document is definitely don't look at the solution until you fight your way through this. That's the best way to learn how to do these kinds of things. And then the solution will let you know if you're on the right track, that kind of stuff. Same idea with section 6.2. I have in this section these exercises that I felt are pretty decent. So you can take a look at those for additional ones. And also these different custom exercises. Same idea in section 6.3. I felt like these are pretty helpful exercises, and these are the additional ones. I'm not going to ask this question. The only reason it's right here is if you can fill this out, and if you can fill it out from memory, then you've probably over-prepared for section 6.3 and you're in great shape. The idea was you just write these in, and that's a great way to start internalizing that information and becoming familiar with how to use it. So I'm not going to ask this question, but it's more just to help you study. So that's the document provided. And again, think of this as pretty much a redo of everything we did for exam one, leading up to exam one, just different content, slightly updated documents. Other questions or comments or concerns about upcoming exam? Okay, just one last thing. I won't remind ourselves about this on exam 3, but it's a good reminder to do it now in the course. Our class is kind of weird. It's a hybrid class. It's really 2 classes running concurrently. Section 22 is fully online. And so for those folks who come in fully online, most of them are on the Pocatello campus, but I've contacted the far remote students with arrangements for your exam proctoring. For other people in this section, the process will be, I'm going to send the exam 2 over to the Pocatello Testing Center. I intend to do this tomorrow. After I send it over, I'll directly contact you to let you know you can call up the testing center to schedule your exam. They want me to send the information first before you call in, so wait until I email you and then you'll be all set to schedule your exam. For people in this section, our exam is going to be officially on this time or this day and the normal class time from 7 to 7:50. That means for people on the online section, you can take your exam earlier in the day on Tuesday, but no matter what time you take your exam, we won't have an official class on Tuesday. We'll just be doing exams and that's it for that day. Well, that's my spiel for announcements to start us out today. I should be looking at the exam too. I'm on the wrong spot on Moodle. After we complete that exam, we'll still do our Thursdays class because it would be weird to lose another day. But after that, we'll be on spring break. So this will be our breathing room. If you're behind on anything, maybe you didn't finish an assignment here or there, I will still accept them for credit. So think of this as a catch-up week if you'd like. I'll still be available by email, but I typically only check it in the mornings. But you can contact me for help with your work if you're working on spring break as well. I think I've said all that I wanted to say. Any other questions or comments at all, folks? Okay, well, this is a pretty jam-packed course. We don't have review days built in, but the one thing I do with this course is I only put things on the exams where I have the opportunity to grade your work and give you your feedback. That's why section 7.1 is going to be on the 3rd exam, but we still have to take a look at it so we're not suddenly completely behind on the course. So here's how this section starts. We're taking a look at not the geometry of trigonometric functions in chapter 6, plotting them and such. What we're doing now is sometimes called, and let me spell it first correctly, analytical. I need to spell that right. Trigonometry. We're doing analytical trigonometry in the sense that now it's all about the algebra, the formulas and the identities that we can use to solve different kinds of problems. We'll be looking at equation solving, but I did change the title on this one. Section 7.1 was officially called Trigonometric Identities and Equations. We're not solving equations yet. That's later on in chapter 7. But we are definitely dealing with identities. That's a massive part of chapter 7 in analytical trigonometry, knowing what your identities are. And we've seen loads of identities. Here's a bunch of them. In this sense, section 7.1 is kind of a review of chapter 5. We have the 3 Pythagorean identities we'll use quite extensively in this section. I wrote here anything that's highlighted in yellow are things that we do have to memorize for the purposes of the course. So for upcoming exams, these won't be provided, but we'll use them so often that you'll probably dream about them. There are going to be things that we use quite often. The reciprocal identities, that one was, in a sense, a type of exam question, essentially. In a slightly different format, this is just a reminder that sine is the reciprocal of cosecant. And same with the quotient identities. Anything that's not highlighted here are things that, if I did make a big exam question with, I would want to include this as some extra support on the last sheet of the exam for the notes. And same with this one right here. So we're looking at identities quite a lot. But that means if identities are such a big deal in chapter 7, we need to know exactly what we mean when we say an identity. So that's the purpose of this example. Let's start off with this one. There's nothing really amazing about these equations. They're kind of simple and fun, but we're trying to get at the heart of what we mean by an identity. So if you look at an equation like 2x equals 8, it's all about what makes that statement true or false. If you think about the ordinary algebraic technique, you just divide by 2, and x would be 2. But then we call this conditional because the truth of this statement depends on the condition x is 2. If x is 2, the statement is true, and if x is not equal to 2, the whole statement is false. So that's the only reason we call those equations conditional. And it's kind of a vague term. Most of the equations you look at are considered conditional equations. It's rare to look at one like this. It could happen in an algebra class, especially introductory algebra classes. But it's good to know when you're dealing with an honest-to-goodness contradiction. So a conditional equation is sometimes true, sometimes false, depends on the value of x. But a contradiction is a statement that is always false. Let's get a feel for this one by attempting to solve it. You could solve this one by maybe adding 4 to both sides or subtracting 8 to both sides. But what I would do right away on this is subtract 2x from both sides. That's probably the sensible thing to do. If you can eliminate x, you might as well do it. So let's write out minus 2x minus 2x. The equation is now the statement that 8 is negative 4. But this is always false. And did it depend on x? Absolutely not. Pick any number you like for x, maybe a 1, and you'll come up to the same kind of contradiction, just non-equality right here. So this is always false. The falseness did not depend on x. And that's what makes this one a contradiction. It has nothing to do with the value x takes. It's just always a false statement. It's a total lie, no matter how you look at it. Those are the contradictions. And in a certain sense, the contradiction is the opposite of the things that we want to study. The identity. An identity is a statement, well, it's the opposite of this one. It's a statement that is always true, and it also still doesn't depend on x. No matter what value x you pick on this, you always get a true statement out, no matter what. That's what we refer to as an identity, and that's why we think of these as identities. No matter what value you pick for theta, any number you like, if you take sine squared plus that theta, cosine squared plus that theta, you will get one, no matter what. Trigonometry doesn't compromise with this. Sorry, say again? Actually, this one is a good one for that kind of question. We proved that one by saying the definition of trigonometry functions themselves depended on this. X squared plus y squared equals 1. So we started with that object, and then we said, pick any value theta you'd like. I'll just draw it this way because it's easy to draw. But then, right there, you get coordinates x, y. But the x coordinate is cosine theta. The y coordinate is sine theta. And so the cosine theta, sine theta get plugged right back in here. And there you have your Pythagorean identity. That one's the hard one to prove, actually, because it goes all the way to sections 5.1, 5.2. It's the core definition of trigonometry. But the other ones, all you have to do is divide by sine squared on both sides to get this statement. Cosine squared on both sides. Let me make sure here. Divide by cosine squared on this entire statement here. Well, you'd have sine squared over cosine squared. That's a tangent. Cosine divided by cosine will give you a 1. And 1 divided by cosine squared, well, you could just say that's a secant squared. And there you have a secant squared right there. So these are all proved in a kind of a nicer way. Those are the kinds of proofs that we're going for with identities. But that one right there, that one's how you get a toehold, and it came from the original core definition. So it's a statement that's always true because that's how cosine and sine were always defined in a certain sense. That's what made it an identity there. Other questions or comments so far? Okay, so we love identities in mathematics because, like we said, there are going to be statements that are always true if they're an honest identity. And so you can do lots of great things with that. You can take something complicated, simplify it way down with the right trigonometric identity. That's something that happens all the time in a calculus class. Sometimes a calculus problem is stated in a way that you just can't attack it, but the right trigonometric identity can change the format of your problem, and suddenly all your tools in a calculus setting become available to you. So in a calculus class, this stuff is used all the time. Let's get back to this. Conditional means it's sometimes true, sometimes false. Contradiction is a statement that's always false. And my claim is this equation here is always true. Let's find out why. On the left-hand side, you can divide both sides by 2 to get x plus 8 equals x plus 8. And now you might notice the tricks. These examples are pretty simplistic. They're just really talking about the definition, nothing crazy with the equation. Same thing happens here, just subtract x from both sides. You get a statement 8 equals 8. But this one is always true. And you can check yourself. Pick any number you like. Maybe it's 10 or 12. Plug 10 or 12 here and here, the same value. Simplify both sides, and it's always going to be a true statement, no matter what you do to this. So this is always true, and the truthness did not depend on x, not whatsoever. Any x you pick is fair game, but you still have a true statement. So that part right there underlined is what made it an identity. Well, I feel like, again, these are not the most amazing equations at all, but we're going to talk about trigonometric identities. We need to know exactly what we mean when we say that. This is what we mean. An equation that is always true. Any questions at all, folks, with these ideas at the moment? Okay, well, we're working with trigonometric identities. The ones we want to be really familiar with, just as a reminder again, are anything in yellow. These are things that are not guaranteed to be printed on exams. We have to have common knowledge about them. So they might be things you want to put, say, on a note card just to refamiliarize when you're doing problems in 7.1, 7.2, and so on. But then going down below, we're going to use the trigonometric identities we saw above to start simplifying expressions. To me, this is really the major takeaway from section 7.1. Sometimes in other coursework, maybe it's calculus, engineering, something along those lines, your work gives output that's just awkward to work with, like this right here. We need to know how to simplify these down to be more efficient if there's more steps coming up. So now we're going to give this and try in earnest. We're going to simplify the expression. And in section 7.1, there's a definite trick to this. For essentially all the problems on these notes and the problems that I'm going to assign, this is a good idea. Express all functions in terms of sine or cosine. If you could do that, a lot of times everything gets kind of resolved. You can see what cancels, you can see what terms combine. And so that's how we're going to start this one. Except there's an additional problem. If we're going to try to simplify the expression, the inputs to all the trigonometric functions ought to be identical. That means when you see this, that's actually a big problem for us. We can't allow a cosine x to interact with cosine negative x in the typical way, all due to that negative x. But exactly, we'll use the even odd identities right here. These are kind of sneaky identities you don't use all the time. That's why I didn't highlight in yellow. If I write an exam 3 that uses these in a major way, I would include this on the actual exam 3 sheet at the very back. But just like you said, if you see a cotangent of something you really don't like, maybe the negative is in a weird spot, well, cotangent's an odd function, much like the sine function is. You can take that negative and just reproduce it right here. So that's going to be our trick on that one. That whole equation is just going to produce a negative there once we make that an ordinary x. So it turns into cosecant x plus cosine x. And here's the change, negative cotangent x. I want to be honest, I don't like the way I wrote that. It's almost like I forgot to put the negative sign right there. In fact, I did. It forced me to put parentheses around here, and if I drop those parentheses, I'll fix it in a moment. That's totally incorrect. Now I'm saying I'm subtracting the functions, but they are truly multiplying, even if I use the identity. So I'm forced to put parentheses here, and now I'm going to do what you said earlier. I'm going to put the negative into that position. While we do that, let's also use the hint in orange right here. Any volunteers for what cosecant is as a function in terms of sine or cosine?
1/sine.
Exactly. When you see cosecant, just think 1 over sine, like you said. So that's a 1 over sine x. Then I'm going to try to remember my negative right here. I'm going to place it way in front so I don't get mixed up with subtraction. We're really multiplying cosine x against this cotangent. How about another volunteer for cotangent? What's in the numerator of this one?
It's a cosine over sine x.
Good call. So cotangent means cosine x. Honestly, that's kind of the way I try to memorize these. If it said co and it said cotangent, the co function should go to the numerator and then the sine function should go down below. So we've got it, folks. We've corrected 2 issues. We took the negative x and just produced a negative right here to correct that. The other issue is everything that was not a sine or a cosine, we just used the identities that we're familiar of and wrote them in terms of sines and cosines. It's still not simplified, but you know what's looking better? This has the least common denominator. I don't like that word, it's really long, but we've got a least common denominator of sine x. That means we can make one overall fraction with that denominator. We didn't need to do any corrections on there. We'll have some problems where we do have to find a least common denominator to work to get to this step, but that's a freebie, so we'll take it. The numerator will be 1 minus it's cosine times cosine, so we'll throw in a cosine squared at x. Now, it's still not done. There's actually a good amount to do at this stage. But any questions to get to that point? Okay. At this stage, we need some extra motivation. There's something extra we have to do here to make this problem work out. And there's actually a good hint. The hint is this right here. Power 2 on a cosine, or a power 2 on a sine, or a tangent, or a cotangent, or a cosecant, or a secant says something about the next thing you ought to try. You see a power 2 on cosine, you should think this. It looks like that Pythagorean identity will apply to this problem. So I'm going to just take that and copy it directly down below. So we have a 1 minus cosine squared, and we do know that cosine squared of x plus sine squared of x equals 1. At this stage, let's use some color coding to connect the dots. We're going to eliminate that cosine squared. And the reason for doing that is, if you can make this look like a sine function where it's highlighted, you can cancel with the sign down in the denominator. So back over here, that's one single identity, but these are like ordinary equations. They're always true, and you can rearrange them. We're going to rearrange them for our purpose. Let's solve for cosine squared by subtracting sine squared from both sides. We will get, once I get the pen tool loaded up, we will get cosine squared of x equals 1 minus sine squared of x. And so that cosine squared that was highlighted, we're going to drop in 1 minus sine squared into that position. So here's what it looks like. Let me know if you have any questions with this substitution. From up here, we have 1 minus copied in. Cosine squared, we'll follow our nose right here. We use the identity, and we rewrote it as this. 1 minus sine squared of x. Then the whole thing is divided by sine of x. But now after we've done all that, there's some cancellations. The 1 minus 1 is going to cancel. That's going to leave a negative sine squared divided by the sine x right here. But before I do any of that, there's one pretty major mistake. Anyone see what the mistake is? Let's use this pen to identify it. Good call. The moment I took something like this and substituted in things with multiple terms, I need a parenthesis here and here because that negative sign must distribute inside for this to all work out. So that's a good one to catch. Definitely don't make that kind of mistake. It'll throw off all of your algebra. Now we're ready to proceed by simplifying the numerator and doing our cancellations. So up above, there'll be 1.
Yeah, can we just make it easier by like doing it at like 1 minus cos square x is equal to sine square x?
Yeah, I think that would be a great way to go as well. So you could also go from here, try like Hayes said, if you have a 1 minus cosine squared in the whole problem, you can think in these terms. Take the whole thing and write in from this identity, 1 minus cosine squared is just simply sine squared x. So that one would work equally well. In fact, like you said, less steps. I don't have to worry about distributing that negative through. And the good news about this is everybody gets the same exact answer, no matter if you use that substitution or if you use this substitution in blue. So I encourage you to try different ways. And in fact, you'll find with a lot of these problems, there could be as many different solutions as they are in people in class right now to the same problem. That's kind of wild in a way. It makes grading interesting because I have to read your work very, very carefully. Sometimes a long solution is totally correct. And sometimes a really fast solution like this one is sometimes the ideal way to get through a problem. Try to take the least amount of steps possible. Let's keep on going this way just because we are now invested. We have to resolve with the rest of the problem. But that's a great approach as well. Other questions or comments so far? Okay, so if you went this way, I now need to distribute the negative through. I'll get 1 minus 1 plus sine squared of x. And then the whole thing, let me just put a quick border here. Everything on the right is scratch work supporting us. Our solution's on the left-hand side. Now here's the cancellation we were mentioning. Those two cancel off. So now we've got sine squared of x divided by sine x. And this is where both solutions would converge. We'd both end up in this location after that cancellation. Now, if you have sine squared divided by sine, the powers cancel. And you just get sine x altogether. So we did it, folks. That mess of a result right there, and you can see those results in other larger problems in different courses, it was just an ordinary sine x hidden there. But we had to go through the motions to really reveal it.
Where did the sine squared x come from in the denominator?
That's a great question. It went from sine x to sine squared x. I think that was a weird copy error right there. Let me see if I can correct that. Should have been a sine x.
Oh,
I should have copied it directly here to here, but somehow I must have been having different thoughts. Maybe I micro sleeped at that moment or something along those lines. And I expected to miscopy it here, but somehow I got it right. Weird. Sorry for that confusion on that step. Other questions or comments at the moment? Okay, so this is the world of trigonometric identities. We used this identity here, or this identity as a competing solution, a little slicker solution, to simplify this down to that. That's the major takeaway of this section. In fact, we did a little bit of that in section 5.3, but now we're starting to do a whole lot more.
I just have
Let's
a
give
quick question.
Yeah, go ahead.
Just how did you in the second portion of that problem where you got the negative cosine x? How did you get negative cosine x versus like positive cosine x?
Well, the negative right here
Uh-huh.
came from that cotangent, the negative cotangent. What I did is I
Okay.
took the and moved it out in front. But the negative that came from right here, I mean, that one's kind of weird as well. That negative came from the negative inside that cotangent. And then we used this identity right here. We used the odd function identity for cotangent to pull out that negative sign. So it went from here to here. And then I just moved it over to the front of the whole product right there.
Oh, okay. I gotcha. That makes sense. Thank you.
Glad to hear that. Other questions at the moment? Actually, I do think I want to leave this filled in because again, this is pretty tricky right here. Giving that negative sign, moving out in front. It was all about these identities right here. Well, I think we're ready for another one. So that was our part A. The major ideas with part A was we had to add a fraction. So we had to observe we had a common denominator. Then we used the core Pythagorean identity to simplify further. This one has other algebraic issues we have to navigate. So let's take a look at part B next. But same kind of trick on this one. If you see a negative x here, the even and odd identities are going to allow that negative sign to move out in front. But when it moves out in front, it's going to cancel that negative sign. So the whole fraction is truly just positive in the end. So this one's going to go correcting that very first step. I'll have just a sine x. So I did two things at once, really. I moved the negative out, and that negative canceled with this, and so it's just gone. Then I'm just copying everything else. Cosine x goes in. On this one, we can just start writing things in as sines and cosines right at this stage. And secant is 1 over cosine. Notice what that implies. You actually didn't need to write cosine 1 over cosine. If you observe that cosine and secant, that's an automatic cancellation right there because you can cancel this way. We're writing it in just to show the steps involved with that, but if you took that shortcut, I'd say it's an appropriate one to take. So we handled the secant function. This one turned into 1 over cosine. Next is cosecant, but same kind of game with that one. This one is just a 1 over sine x. Next one is the tangent function. There's no cotangent on this one, so the numerator should just be sine, not cosine. So sine x over cosine x takes care of that one. And then down below, well, just like on the last problem, you have options. You can take that cotangent, multiply in front and make it a tangent, or you could just leave it in the denominator and work with it later, or go with the route of leaving it in the denominator. It's not the slickest solution, but I think it's the easiest to read in the notes. In the denominator, that cotangent turns into cosine x. Divide by sine x. And now we're ready to get started doing our cancellations and that kind of stuff. This to me is the major step though, writing everything in terms of sine and cosines, as well as handling that portion of the identity. Just to make the notes more specific, let me take this right here. Since honestly, without this one idea, there's no way I'm going to get to the right answer. We had to make every single input identical, look like X, to start canceling things appropriately. Any questions at the moment, folks, to this stage? Okay, well, here's our reward for our hard effort here. When you see this sine X, it is multiplying 1 over sine X. You can rearrange these things if you wanted to exhibit it. Or here's the big punchline. They immediately just cancel off. They're gone. Likewise, cosine times 1 over cosine, that's just a cosine divided by cosine. That's just a weird way to write the number 1, so that's canceled. I don't have a cancellation here, sine X over cosine X. So we're just going to have to deal with the remaining survivors of this thing. Start by writing this in, sine X divided by cosine X. We're dividing by a fraction, so the other algebraic idea is just multiply by its reciprocal. So times sine X over cosine X. Now there are no cancellations left over, but we have like bases. A sine multiplied by sine would give you a sine squared. Likewise, in the denominator, you've got a cosine squared. This feels like a good stopping point, but it actually isn't. There's still one additional thing we need to do to this thing. Anyone see what the end answer ought to be? Exactly. It simplifies further by observing sine over cosine's tangent. And so sine squared over cosine squared is tangent squared, as you said. So this ridiculous mess, which does come up in mathematical work in ordinary classes like calculus and engineering, was just a weird way to write tangent x. Again, we have to understand the trigonometry to reveal it is really not as complicated as it appears.
So like
Well,
this kind of problem,
yeah.
oh, sorry, excuse me. So like this kind of problem, would you like, what answer do you want? Do you want us to leave it in like sine, cos, or tangent, or like any of the trigonometries, but like simplified version? Like it can be
Simplified version.
Not only sine,
Right.
cos, tangent, right?
Yeah, that's one way to say it. So if you have something like this, for example, it's not considered simplified until you write it as secant x. Same issue here, if you have a sine over cosine, not simplified until it's a tangent and that kind of stuff. If you had a different version that went like this one's not considered simplified. The simplified version would be cosine x. So we're trying to get it down to one function, and we prefer that function be in a numerator if possible. Turns out it's always possible with trigonometric functions. Does that make sense with that question there?
Yep, thank you.
I have
You
a
bet.
question.
Yeah, go ahead.
So say that we do leave it as a fraction. We'll say 1 over cosine. Would you give us half credit then if we don't complete it all the way, like put it into its actual pure function?
Oh, that's a great question as well. I would give you almost all of the credit, honestly. Let's suppose, for example, say in this scenario, this was a 5-point problem, but you stopped right here and didn't produce tangent squared x. I'd probably just write on your paper something like this, -1. It should be tan squared x like that. So you're not losing too much credit by missing that very last step. It's more of a kind of a reminder that there was one more thing to do. And same kind of comment, if this was some kind of long problem, let's say this is a 5-point problem, that you stopped here, you probably are only going to lose a single point. Other questions about that at the moment? Okay, even though it's 1 point, it still kind of stings sometimes. If it was a real exam problem, my exams are sometimes out of like 50 points and things like that. One point on exam is actually pivotal. If you made this mistake, leaving it as a 1 over cosine x, it might be something like you lost a half a point. On homework questions, you might lose 1 whole point, but those are weighted totally different through the syllabus. And that's the value of these kinds of things right here. It's also why we had that exam question on exam 1 of write out tangent, write out cotangent and such in terms of sines and cosines, because all that stuff comes way back and we have to be familiar. These are the simplified versions. The things on the right-hand side are the things we're trying to simplify out of. You know what? I think that's a good concept to think about. Think of this left-hand side as simplified. The right-hand sides with the fractional versions are not the simplified versions. It's these things what we're trying to get to. Other questions about those questions at the moment, or other questions? Okay, well, let's go down. I think this one, in my opinion, is a pretty challenging one, but it's a little bit nicer in that we didn't have to grab a random Pythagorean identity to navigate through it. To me, those are sometimes pretty challenging in their own right, but that's how simplified goes. And sometimes when it asks you to simplify things, there is a hint. Some of these are in the actual homework assignment, and here's what it would look like. We're going to simplify this thing. It doesn't necessarily look like a lot of good directions to go on this, but the hint is our end answer will involve secant x some way, somehow. It could be 2 times secant x, or maybe secant x itself is the answer. It just has to be simplified in terms of a secant function. So let's make this our next one to tackle. It's a hard one to start in a certain sense because, well, I can't do anything with that fraction. It is in terms of sines and cosines. The only thing I could do is change that one. That's a sine x over a cosine x. So let's make that our first step. First, I'll copy the problem so we know where we started. Okay, that's the start of the problem, and here's where our solution begins. Still, I have no idea what to do with that fraction, but here's the thought algebraically with this one. If you're simplifying, and there's a fraction right here, you're probably going to want to convert this to a fraction somehow, some way, and add together the 2 fractions, finding the least common denominator. So to start on this one, let's write in cosine x. We want a really large fraction bar. We're going to be inserting stuff. Denominator is 1 plus sine x, but it's going to need a parenthesis as well. Then plus, tangent is sine x over cosine x. I did want to park right here and mention one thing that I sometimes do notationally. I like to write cosine of x whenever I can, because it's nice to just be clear about the function notation. But if there are multiple parentheses, I often take a sine of x and write it this way, just sine x, so that I have no issues with multiple parentheses. So I often write it in those kinds of terms. Now, next thing we need to look at is we need to produce the least common denominator, but it's not as bad as it seems. We just go over here and decide what's missing. We're missing that factor, cosine x, so we throw it in. So that corrects the first term. Then we go over here. It already has cosine x, so we're not worried about that. What's missing is 1 plus sine x, so we throw it in. Sorry, say again. Do it in. Oh, I see what you mean, like a cancellation of some kind. You know, that's actually a way people prove some of these identities. Sometimes people have shown that if the derivative of the left-hand side is equal to the derivative of something else, they only differ by a constant. If you can prove that constant is 0, people do in fact prove trigonometric identities in that kind of way. So that's a valid approach actually through calculus. Other questions at the moment? Okay, well, we've got it, folks. In this process, we just produce the least common denominator by following our nose. Complete the denominators by including what's missing, numerator and denominator. And then all we now have to do is add across the numerator, maintain that common denominator. So let's write in 1 plus sine x times cosine x. This numerator converts to cosine squared of x. We're adding across, so plus, and over here, we need to do a distribution. This will be sine x plus sine squared x. Now that we've gotten to this stage, there is something in there that's glaring at us really, really loudly that we need to spot. Anyone see what it is?
Sine
It's in the
squared
numerator.
plus cos squared x is equal to 1.
Exactly. The moment you see a cosine squared, be on the lookout for a sine squared. Because if that emerges, those two pieces highlighted is just a glorified 1. Your numerator is 1 plus sine x now. Let's write down the identity. The identity was through cosine squared of x plus sine squared of x. And let me move the participation window just a bit. Sorry, folks. Equals 1. So we're just going to insert a 1 right here and call it 1 plus sine x. But notice how pivotal that is. The purpose of the identities is not just using them, but also spotting them. That's half the battle sometimes. Now this turns into, I'll leave this 1 in blue to convey that's what we substituted, plus sine x. The full denominator is 1 plus sine x times cosine x. And now we have a really big cancellation. That 1 plus sine x now cancels into the entire numerator. The numerator is not gone. There's a 1 left over. I think I made that mistake at one point in the class. So let's start by putting that 1 there. It's not gone. The denominator is cosine x. And if this was a 5-point, say, exam 3 question, you could lose potentially a half a point stopping right here. There's one more step. Any volunteers for what we should say next?
Secant x.
Good call, folks. So secant x, stated in class and over Zoom, gets us to that end answer. We did it, folks. And we did, in fact, write it in terms of secant x. They essentially gave us the answer. Your answer is secant x. Now, these instructions don't mean it always ends at secant x. It could have been secant x minus 1, secant x divided by 3. What they're indicating is secant x should be the only trig function left after you simplified. Sorry, say again. Any multiple of pi, so sine 0, sine pi, sine 2 pi, would result in an output of 0.
So is that secant, it gives in terms of secant x, but like our answer is like secant x, but some questions it won't be like that, right?
Yeah, it could be like 5 times secant x, and that's still valid.
Okay.
Other questions or comments with this one? Okay, well, we definitely cracked open section 7.1. It is a longer section. We have more things we want to do. And this is the second part. We're going to prove our own trigonometric identities. I have a lot to say about this because the one massive thing we want to avoid as people working in mathematics is anything that looks like circular reasoning. So I'll make a big deal out of this and explain why it's a problem. We're avoiding circular logic. We'll show how to prove that's an identity right there, that the truth of that equality had no way to deal with the value of theta you actually plugged in. Oh, that's a really good question there. One thing that I kind of glossed over is when we say identity, we're only talking about the values of x in the domain of the whole expression. So if sine is down below, we're only picking values of theta that avoid anything outside of the domain. But yeah, that's a good question on that one. Any time of identity that involves, say, secant, tangent, cotangent, and so on, they always have undefined values. We can see them on the graphs through the vertical asymptotes. So when we say identity, we mean all values of phi or theta or what have you that is in the domain of everything in the whole expression. So we're not as worried about sine going to 0 because we're going to be avoiding angle 0, angle pi, 2 pi, and so on. Other questions or comments about that at the moment? Okay. Well, thanks for all the participation, folks. These are exactly the right kind of questions you want to ask for these kinds of material, and very insightful questions as well. Definitely don't want to keep you too long. The class is over and roads are not great. So we'll be right here on example 3 when we return next class. Any last questions before we wrap it up?
No, thank you.
You bet. Have a good one, folks.
Thank you.
Take care.